and we all are aware about his teaching style and how insightful sessions were. Already we have attended many of the sessions earlier in the series also. Okay, so definitely, I hope this session will again be very much fruitful for all of us. So, and request all the participants to kindly keep participating in the discussion whenever we are having some break. Go through some whatever discussion had been made, and try to come up with some question or doubts that you have and put it in the chat box so that sir will answer it. So, with this, I would like to welcome Dr. Mustafizur sir to our session again. So welcome you, sir, and over to you.
Thank you so much for the kind introduction. I hope I am audible, right? And the board is visible,
Yes,
right?
yes, yeah. Blackboard is
Thanks.
visible.
Yeah, thanks. Thanks a lot. So, of course, it is like thanks to the participants who are managing time from their busy schedule. They are already teaching in colleges and managing time to attend these sessions. And I know that the topics that I am taking, the probability, linear algebra, last week I took, right? These are very fundamentals and very basic things that you already know, right? So it's challenging sometimes, right, to cover these kind of topics. But at the same time, I also get a chance to recap all those things, right, and try to connect how they are so I mean useful in quantum computing in various contexts. So two things. One is I'm referring some books. So one particular book is the probability, random variables and stochastic process. So this is written by um, A. Papulis. This book is self-sufficient to cover most of the important part like random variable, random process, various random processes, stochastic processes, right? Like ergodic process, and their use cases not only in quantum theory but like in general engineering and scientific context. So this book is very important. Although there are other books like De Moivre and other books, so you can have a look, but this one is pretty good. And the second book I'll refer, maybe I'll come back in some other QT or some other program when we'll talk more on the quantum communication side, right? Quantum information and quantum communication, and there is a direct applications of quantum the probability in quantum computing or communication context. So another book that I'll refer as quantum information theory, by Mark M. White. Mark M. White. These two books are good enough for the sessions that I'll take today and tomorrow. And I have shared some notes. Maybe today or tomorrow after the class, you'll be getting the notes and some quick questions. Very simple thing. So so this is like all about the material, and then I'll also so demonstrate some Qiskit Qiskit programming or hands-on related to this topic. And I assume and I believe that you all already participated with Dr. Ritojit sessions, right, my colleague, and he is a wonderful speaker and lecturer. So he covered I think most interesting parts like error mitigation thing, right? So so you already know some context. There is no at least once you already know that how to fight with noise, right? But still, we'll just go back and polish some of the topics, right? And see, this may seem to be very easy and very basic things. Okay. So some of the topics that first initially we need to recap, although I am not covering this topic, I will refer to some of the lecture series that MNIT AICT course already available on YouTube. Okay, please please revisit those courses by MNIT YouTube channel, and you will find my videos there and other speakers videos on these kind of topics, right? So the foundations of probability required for quantum computing. Just mentioning some of the topic names so that you can when you revisit the lectures, so you can just directly look at those topics. Okay, so important topics that at least, I mean, although the it is like, as much as the probability and statistics theory you have a background, it is good to directly go in the quantum computing and dealing with quantum measurement, noise, post processing techniques. But at least somebody has to know what is random variable, right? So basically, if you have some any abstract phenomena, right? Abstract phenomena, and that abstract phenomena, if you can define with some discrete or some continuous variable, right? So say, for example, if you are tossing a coin and that is an abstract phenomena, and the outcome of that experiment can be head or tail, right? And then you basically define it with a set S, right? And you map this abstract set to a real number set, right? Real set. So set of real numbers, right? For example, you define head with say +1 and tail with say -1, which has say mathematical notions, right? Or 0 or 1. So basically a functional map from S to R, right? So that you define with the function, and that particular function is called random variable, say X, right? So this is one important context. And if the random variable basically takes some discrete values, right? Discrete values, and those discrete outcomes may have some associated probability. For example, probability of tossing a die, right? Six-sided die can be maybe 1, 2, 3, 4, 5, 6 out of this set, right? These are the, so it can take any probability, but if you do measurement for many times, so theoretically the probability of individual particular X taking a particular value, say one is should be capital X, one should be little x, right? For example, so the mathematical abstraction can be, for example, this is x1, x2, and to x6, right? Any particular xi, and the random variable you define x. So x taking xi value, and the probability associated with this theoretically 1 by x, right? 1 by 6 in this particular case, right? So I mean, if x takes discrete values, so there is an associated probability, and the probability versus the random variable versus probability, if you plot, you get something that is called the probability mass function. Probability mass function, or PMF, right? And this is extremely important in quantum computing, because when you represent a quantum state get psi, right? And it may have say say A1 get 0 0 plus B1 get 1 1, right? Plus C1 get 0 1 plus D1 say it is 1 0, right? So these are the 4 possible states, right? And basically you repeat the experiment through some algorithmic process, right, to basically do the superposition interference on all those coefficients, right? And you see what are the probabilities in the 4 bases, right? 0 0, 0 1, 1 0, and 1 1. Last week we have seen these are basically column vectors, right? Now and also we termed this kind of terminology such orthonormal basis sets, right? Orthonormal basis sets, or computational basis, also known as computational basis, right? Also known as standard basis, right? So these are the terms we defined last week. Now they are simply all these, by a bit string. So suppose you have a certain number of qubit, q1, q0, q1, q3, q2, q3. Suppose you took four qubits, and each particular qubit can take values, say 0 or 1, right? So individually, this bit string that is starting with 0 0 to 1 1, right? With 0 1 and 1 0. So this is now becomes a random variable, right? And each random variable has an associated probability, right? For example, this 0, 0 might have the probability a square. So this is a1 square. A1 is the amplitude of a0, 0. So the probability is a1 square. Similarly, say it is c1 square. This is d1 square. And this is, say, your b1 square. Now, your purpose of the algorithm is to basically manipulate us. So this is, suppose initially you have a wave function psi1, and it has a associated say probability description PMF, right? 1. So I say P1, right? So later and then you applied some algorithm, right? Some Grover search or whatever it is, and you come up with an basically updated state gate phi, right? And you see the probability distribution change from P1 to P2, right? PMF, probability mass functions change from P1 to P2. That means you manipulated the probability, and probably maximize one of the probability, and other probabilities you kept low or 0, right? That's your objective, to find your solution at 0, 1 state, something like that. So basically you deal with the probability amplitudes, right? And how you manipulate the probability amplitudes is how you design this U or the quantum circuits, right? So that's why this probability mass function is extremely important, right? And later tomorrow, today I won't introduce, but tomorrow we'll introduce something that, suppose your quantum state has it may not be pure quantum state, right? Or your circuit that you are designing using certain quantum gates, right? They may be noisy quantum gates. So sorry. So the state, quantum state that we defined using column vectors, right? Today we'll also tomorrow we'll also define something called a density matrix. Density matrix, which will capture the uncertainty in gate psi. So suppose you prepare multiple gate psi. Suppose multiple quantum state you create. First you create a gate psi 1, which has a associated probability P1. Then you created another the same state again, and it has a probability P2. Means you created multiple times same state, and you see how many times it is repeated with what representation. So how you can capture the associated probability in that particular state, right? So we'll define a density matrix tomorrow. This is not only used for the noisy case, but noiseless case also. You can define a density matrix as a as a outer product of the column vector like this. Sorry. So this is for the pure state, and tomorrow we'll see the basically for the noisy state or impure state, you can write in this way. Okay. So this is very similar to how you defined the expectation value. We'll define what expectation value means in quantum computing. Although I believe Dr. Ritojit already covered things and he demonstrated on Qiskit, right? And we'll see the same things with more examples here. Okay. Sorry. The next topic is so this is about the random variable, and if it takes the discrete values, right? Then we define something called the probability mass function. And similarly in Qiskit, you will see the histogram plot of quantum states, right? They are the mathematically the same thing. And now if x takes continuous values, for example, temperature of a day, okay? So which can be any continuous value, right? Between a range, say 20 degree to 35 degree, something like that in India right now. So there is an associated associated the associated phenomena that describes the distribution of this X, right? So that is defined with the probability density function. Right? Density function, right? Or PDF. So written as fx, and there is something called the cumulative distribution function, CDF, right? So the PDF is not probability, first of all. Okay, it's the density. So for example, if you have a wave function, right, the wave function is distributed like this. It can be Gaussian wave function, it can be plane wave, whatever it is. And so this is psi of x, right? And you want to measure the probability of this wave function between region A to B, right? So what is the probability? Integration psi x dx between A to B, right? So when we measure the probability, normally take the square of the function, then we do the integration. It's give the probability, right? And so that's how all these concept, although I'm not covering. So when you get time, please go through these things. Although the books I referred, you may not directly get the quantum interpretation of the probability thing, but the notes that I provided and available in my previous lectures with M&IT course series, it is already there. So today I'll try to take more computational aspects, not the theoretical aspects. Okay. So third is one is the random variable. Second is the PMF, PDF, and CDF concept, right? And third, okay, and also the quantum postulates, right? All the quantum postulates. So you can check that the quantum state as we represent, right, whether in the superposition state or in a particular measurement basis state. So what are the what may be the possibilities, and sum of the all possibilities should be equals to 1, and that is because to obey the probability law. So that you can directly compare with the discrete probability theorem, okay, or the postulates. Third thing is that is important is various various distribution functions. Distribution functions. It can be discrete distribution functions like Bernoulli, right? Or the binomial, or the continuous one, the Gaussian, gamma functions, etc. And these are required, and in discrete case Poisson also, Poisson process also. So these are important to basically model various noise in quantum computing, and basically guaranteeing the error bound of a particular quantum algorithm, right? The central limit theorem for large numbers, and there is a small topic that I'm not covering, the random number generator, okay, and that's basically taking the probability aspects in the quantum computing context. I shared the note. Please have a look all these things, okay. So now there are more topics I'm not covering, but at least you please look at these topics, and let's start with today's content. In the second half, I'll take some 15 minutes of discrete session. And before that, I'll cover some information theoretic part, very basics. And of course, the probability is associated with this. And tomorrow, I'll cover one teleportation algorithm, quantum teleportation algorithm. And some I'll see if I can cover any such related algorithms like VQE or QA kind of thing. So So simplified context that we learned from yesterday, like last week, is that our quantum states are represented by vectors, right? At least when you talk in discrete fashion, like you want to work on a computer, you need discrete representation, not the wave function representation. So they are vectors, right? And so we denote it by get psi. And then our operations are denoted by unitary matrices, okay? Tomorrow, if I get some time, I'll introduce something called SU2, that is called super unitary, right, of order 2. And this is coming from the representation theory. Representation theory to describe certain quantum operators, okay? So this is sufficient to work on a quantum computer. But in general, representation, generally quantum states this is fine for quantum computing. But once you touch the noisy versions or the you work on the noisy hardware, right? So then you need to also consider that quantum state are represented by density matrices. Tomorrow it will be more clearer what is density matrix and all. Density matrices. And it allows for a more general class of operators, although we'll stick with the Schrodinger isolated quantum system. Okay, isolated quantum system. But in general, if you are more interested, you can look for open quantum system like Lindblad system, open or Lindblad quantum system. Right. So this is when you have a quantum computer and it interacts with environment, right? And there is a quantum channel, which basically you are losing your quantum information because it interacts with the environment, right? So this is how you define your in the total dynamics of the system, right? And when you try to capture the information of only the quantum computer, you take the partial trace and trace out the environment part, right? So this is more important for those who are interested in the quantum info, right? But only for the quantum computing part, this is fine. Like your state is a vector and all your operation are the unitary matrices. Okay. In fact, when you consider noise, there are both unitary dynamics as well as non-unitary dynamics. Now let's first talk with the classical information theory, and then I will slowly come back to quantum information with specific distinction. What are the things that is different in quantum computing and how to deal with those um, with those phenomena, right? So I am not covering the definition like entropy, those things, mutual. So those are available in the notes, so you can have a look. So, and also the textbook I referred. I'm only just covering the conceptual part that will help us to basically dig into the subject. Okay. So suppose X is a bit. Okay. X is a classical bit, and then the set of classical states, I say classical state represented by S, is basically 0 and 1, right? And all the classical computation where we use the bit string, right? Classical bit string, like to represent our daily day-to-day messages, right? WhatsApp, everywhere, like day-to-day emails and all. This ultimately converted to the machine language, right, in binary string, and we denote by 0, 1, n, right, n bit binary strings, 0, 1, n. And suppose let's stick to this part only, 0 and 1. If X is a coin, then the set is head tail. If X is a die, then S is your this set 1, 2, 3, 4, 5, 6, right? These are various like outcomes, right? Six-sided die. So each classical state, so we need to understand that classical does not mean there is no uncertainty. Classical information, there is uncertainty. Quantum information, there is also uncertainty, but with up to which order or what are the special cases, right? That we need to understand. So each classical state has some uncertainty, right? About the outcome. That if I toss a coin, whether I'll get head or tail, the outcome is uncertain, right? And that uncertainty part has an associated, and it has an associated probability, right? So suppose the probability of X taking the value 0, 0 classical bit is 3 by 4, and probability of taking the getting the classical state equals to 1 is 1 by 4, right? So that is the probability of state X, right? State of X. Or it is like, let's write in the correct way. Probability state of X. So typically X we call as a random variable, right? Now, a succinct way to represent the probability, this particular probability state, is by a column vector. Column vector X bar. And the same thing I'll write as 3 by 4 and 1 by 4. Where this first entry corresponds to 0 and second particular entry corresponding to 1, associated probability. This X bar is also known as probability vector, and this probability vector has all the entries should be greater equals to 0, means non-negative, and sum of all those probability should be equals to 1. Means if you take the column sum, right? Column sum, that should be equals to 1. Now, if you are observing multiple such variables, right? And suppose your variables are X bar, Y bar, and Z bar, and you create a system, classical system, which has three randomness of three particular variable, right? And you take some values in X, some values in Y, and some values in Z, right? So the theory is all these individual elements should be greater equals to 0, that means non-negative. And sum of this value should be equals to sum equals to 1. This column sum equals to 1, right? These kind of matrices are called stochastic matrices, right? For example, the Markov matrix, right? All these things are important because I'll quickly go to the quantum part and you will see. Now let's define certain more terms. Although you are looking at these terms from beginning QT-01, and you will this will feel very much boring, right? But let's start it again. It will hardly take 5 minutes. Okay. Dirac notation. Suppose sigma be any classical state set, classical state set, and suppose ket A is a column vector having 1 in the entry corresponding to A belongs to sigma and with 0 for all other entries. Suppose I define a set like this. Okay, so suppose this is now difficult. Let's take example to understand what we just said. That suppose sigma has a set with elements 0 and 1, and we define, so these are individually like small a, right? And we define that a as a vector. When I say 0 vector, that a vector, right? So ath position I have to look like 0 vector, I can write at 1 0, and when it is a 1 vector, so it is 0 and 1, right? Let's take a second example to understand it more. Suppose sigma equals to A, B, C, D. These are the 4 cases, right? And now we want to define vectors like this. Suppose get A is the eighth position is 1, right? So the first element will be 1 and all rest will be 0. Same you define ket B. So this is very similar to elementary orthonormal basis, right? 0, 1, 0, 0. Then ket C you define like this. So third position you keep 1 and all rest 0. So this is the way how we represent a bit string, and then we define a computational vector, right? Or the computational basis set like ket A, ket B, ket C, ket D. And vector of this above particular form is called the standard basis vector. Standard basis vector. Okay. Every vector can be expressed uniquely as a linear combination of the basis vector. So for example, earlier we took a classical example, right? And the classical information was represented by 3 by 4, which was the probability of 0, and 1 by 4, which is the probability of 1, right? So the same thing we can write as a superposition of 3 by 4 ket 0 plus 1 by 4 ket 1, right? Here ket 0 is basically, you can just quickly check because ket 0 is your 3 by 4. It is ket 0 is 1 0 plus 1 by 4 0 1. And this is how we represent the information in a vector representation. So these are the computational basis vector or standard basis vector. Now, if somebody asks you that you have an arbitrary quantum state psi and you want to represent in an arbitrary measurement basis, say HLK, HLK and say M. So you have a quantum system where you know the basis like this. This basis in your particular measurement laboratory, you know these things, H, L, K, and M, and you have a quantum state like this, right? This is get psi. And now you can simply represent this particular projection here, projection here, projection here, and projection in this particular basis, and you can get the coefficients, right? Corresponding coefficients. So this is your sigma set, right? And you can quickly define the sigma as a like a computational standard basis system, like ket H, ket L, ket K, and ket M. And your simply measurement outcome is the probability H, and this one, this one. So you're doing vector products. So any order you can take, like psi this side or that side, and you can take the get the probability P1, P2, P3, and P4. Right. So what happens if we measure the system X while it is in some probability state? So we see a classical state A chosen at random according to the probabilities, right? And this changes the probabilistic state of X, having recognized that X is in the classical state A. So that means once we do the dot product, right? So your quantum state was a vector, right? Vector quantity. And your computational basis or standard basis was another vector, right? And you are doing the vector dot product. So when you do the vector dot product, what you get is a scalar quantity, right? Scalar deterministic quantity. That means there is no further randomness, right? So that means probabilistic state of X, right, from our viewpoint, that basically becomes X is in classical state A, where the probability, once you confirm the state, then probability that X equals to A, you get assured value, that means 1. The probabilistic state is denoted by, and the probabilistic state is denoted by Kt. That means what you get, so once you measure it, suppose this wave function you measure on the mth basis, right? This is your mth basis, and you have a wave function here, right? So once you take the projection on this basis, so you get your answer will be Km. This is your answer with what probability you get Km, right? So let's take more examples to understand this concept. Suppose x bar is 3/4. That particular example, ket 0 plus 1/4 ket 1, right? And once you do the measurement, right? So the probability becomes 3/4 this side, right? With ket 0, and this particular side you get ket 1, right? With probability 1/4. So now let's do two kind of thing. One is the deterministic operation, and then we'll go to the non-deterministic case, which will more clarify the use cases of a measurement operator. So first is the deterministic operation. So every function, suppose you have a quantum state psi, and you want to design an algorithm to reach another state phi, right? Where your solution lies after doing repeated measurement, you try to maximize the probability of that particular basis, right? Now, suppose this transformation is given by a function f, right? So every function f that basically changes this set psi to the set, the same set element it gives, right? it describes a deterministic operation that transform the classical state A into f of A for each A belongs to this the set sigma, right? So how I can achieve this, because my information now it is a vector, right? And another information that I want to transfer, like after the transformation of the quantum state from psi to phi, so that basically transformation is another vector, right? So that means initially I was in quantum state, say computational basis state, say A, and after this I want to reach somewhere in some measurement basis where I am interested to do the measurement. Suppose that is f of A, and that particular state is f of A, right? In chemistry, people do they try to basically represent the wave function into their known measurement basis, like S2O, or it is a Fock state, or whatever state it is, like. So that is after the conversion thing, but they initially start with some computational basis or some particular basis, right? So you want to reach from a vector to another vector. How you will go there? You of course need to multiply with a matrix, right? So this is a unique, basically there is a matrix, unique matrix, right? M, and that satisfies this basically M times this vector, which gives the another vector f of A. So that linear transformation is just done using a matrix multiplication, right? So you need to multiply a matrix which basically transform your quantum state psi to another quantum state phi, right? And this basically transformation with this, the probability associated with this psi and the probability associated with the phi changes, right? So that basically get A to get f of A, right? For every A belongs to psi. So basically, in simple words, if I have some vector x, and my transform state will be x m x bar, where m is the transformation matrix, right? Now let's see some example to clarify this part. Suppose my input is A is I'll take three four types of thing, and F1A, F2A, F3A, F4A. Suppose my input is 0, 1, right? 0, 1 is what? 0, 1 means get 1, right? And what I want is 0, 0. Suppose my input state is, or the initial state is 0, 1, but I want 0, 1, same state. I want to go back to the same state, right? Suppose I start with 0, 1, and I want to reach 1, 0 state. That means this is get 0, right? 1, 0 means get 0 state. So you started with get 1, but you want to reach get 0, right? And suppose I start with the get 1, and I want to go to 1, 1 state, right? In the Cartesian coordinate system. Suppose this is the thing, like this is your suppose 0, 1, right? 0, 1 means get 1, right? And suppose this is your 1, 1 vector, right? So you want to transfer this vector to this vector, right? So then basically what are your this transformation matrix? So the first one will be your 1, 1, 0, 0, right? Second one will be very easy. Can anyone reply this? What will be the you are starting the point and your final state is same state, same quantum state. So what will be the matrix? M2. Somebody needs to tell me M3. We have already seen this example last week. You just need to recall this here. And M4 is basically 0, 0, 1, 1. Can someone put in the chat box what is this M2 and M3 matrix? So the general definition is, in general, if M has columns B and A, that will be equals to 1 if b equals to f of a. It will be equals to 0 if b not equals to f of a. Okay. Yes, so this is identity matrix. And what is M3? Identity matrix means 0, 1, 0, 1, 1, 0, 0, 1, right? What is M3? M3 is the Pauli X matrix, right? That means 0, 1, 1, 0. You just need to multiply this matrix times this vector, and you should get this another vector. So just you need to multiply that. This is that much easy, right? Yeah, correct. So now let's talk about the row vector, right? So this is all we have talked about the column vector to represent quantum state. Sometimes we write in this way, bra, or the Dirac notation for row vector QT-0, which is basically 1, 0 in this row vector form, right? QT-1, this is bra 1, it is written as 0, 1 in this form, right? And then we represent the vector dot product. So these are some notation which will be used later. Vector dot product. So where you multiply a row vector, right, times a column vector, okay, times a column vector in this way. So that means suppose this is your row vector, you multiply with a column vector. And this kind of thing will give you a answer, which is a scalar quantity, right? Scalar quantity. Just you can check. It's a 2 cross. How many rows are there? So there are only 1 row and 2 columns, right? 1 cross 2. And this is 2 cross 1. So it will be 1 cross 1, right? Scalar quantity. Example A and B, where A, B are orthonormal bases, suppose, right? And they can be anything, right? The answer is if A equals to A, then the dot product will be equals to 1. If A equals to B, and equals to 0 if A not equals to B. And especially they belongs to, if especially they belongs to the set sigma. Other cases you will get different results, any scalar results for any other generic case. But if they belongs to the set sigma, because for sigma basically eighth position is 1 and all rest are basically 0, right? For example, the Cartesian coordinate system, right? The R2. So this is your R2 case, it is your say 1, 0, and this is your 0, 1 vector. So if you do a dot product between 1, 0 and 0, 0, you will get basically 0 answer, right? So now let's come to the vector outer product in Dirac notation. So now you have a column vector times a row vector. This is the notation, right? So suppose you start with 3 elements as a column vector and then a row vector like this. That should match the row column compatible. Then you basically get a matrix of 3 cross 3 dimension. Right. So for example, there we'll see a lot of example and which are extremely important. And just by doing the vector outer product, what you have done, you have earlier you had something like QT-0. It was a quantum state, right? Once I say it's a QT-0 outer product with QT-0, now it's a matrix, right? And this particular state can act, now it can act as an operator. Act as an operator. Now, whether it's a valid quantum operator or not, that is another question. But it's an operator. Okay. because it's a matrix and I can apply this to another quantum state k psi, right? So now let's take some example, and the examples are important. First is the 0 0 outer product. Okay, so 0 means 1 0 1 0, so we'll be getting 1 0 0 0. Another name is H, sorry, not H bar, it's H. And this is called hole operator or zero operator, also known as zero operator. Okay, the purpose is, if you apply H operator to get one state, right? Now you are applying this on the quantum state one, right? Your answer will be 0 0. That means it will exclude what is one. One is basically your 0 1, right? And you are getting 0 0. You just simply multiply this matrix with this vector. You see your result will be 0 0, right? So once you get 0 0 means it excludes this one, right? This particular one. So but if you multiply H with get state 0, it does nothing, right? So this particular operation is known as a hole operator from the semiconductor like side. Like this is how you create a hole. And there is another operator called a particle operator. For example, suppose this particular state. This is you can create, and you will see the answer will be 0 0 0 1, and the general notation is n, and this is known as the particle operator or the fermionic operator. Particle operator. So if you apply this n operator to 0th state, it will create the 0 0 state, and if you apply the one state, excited state, it does nothing, right? So basically that means so 0 0 means what is 0 0? 0 0 means 1 0, right? So it excludes the 1 from the upper state, right? And it becomes 0 0 state. This 0 0 state is sometimes called the 0 0 state is sometimes called in physics it is called the oblivion state, right? So basically now there are more two operators which are extremely important in quantum chemistry and quantum physics. So these two operators are very common. One is 1 0, right? This is a simply outer product, okay? And another one is called the 0 1, right? So 1 0 will be 0 1 0 0. This is known as a dagger, right? Also known as the raging ladder operator. Ladder operator. So and this particular thing is 0 1 0 0. You just need to multiply 0 vector with 1 vector, right? And this is known as a operator, also known as lowering ladder operator. So the purpose of this a dagger is if you add a dagger with the 0 state, it makes it 1 state. If you apply a dagger with 1 state, it prepares the oblivion state 0 0, right? And if you apply a matrix, this a operator on 1 state, it just does the opposite. It will make it 0. And if it is a is 0 state, it will make basically 0 0, just opposite of this two part, right? So these are also known as the annihilation and creation operator in chemistry. Okay, annihilation operator, annihilation and creation operator. Earlier we had the Pauli X operator, right? Pauli X. So what is the Pauli X definition? Pauli X is basically sigma X is written as 0 1 1 0, right? And what it does, it basically sigma X, if you apply, to 0 state, it makes 1. And if you apply the same operator on one state, it makes 0. That means it's a unitary matrix, right? Unitary operator. That means sigma x dagger, sigma x each identity matrix, right? But in this case, the both the properties does not hold. So none of them are unitary matrix. So if you multiply this matrix with the same matrix, you won't get identity matrix. So they have special purposes. For example, the A matrix can also be written as the lowering ladder, can also be written as half of Pauli X time I of sigma Y, Pauli Y matrix. And A dagger can be written as half of sigma X minus I sigma Y. So now you represent your non-unitary matrix in terms of the summation of the unitary matrices. So these two matrices you can basically evolve on a quantum computer using this particular breakup, but particle and the whole operator are difficult to emulate on the quantum computer because until and unless you can represent them in the proper way, unitary way, then it's difficult. So the general part is n plus h is identity. A dagger plus A dagger A is identity. They are not unitary. Okay. They are sometimes called singleton operator. Now you can ask me what is the purpose of this. Although I don't have background in chemistry and all, but in general, if it is your ground state, say ground state, and suppose this is your excited state, right? First excited state, and the ground state you define as K0, and your first excited state you represent with a vector K1, suppose energy level, right? And suppose you have an electron here, right? Suppose you want to basically jump the electron from first excited state to the ground state, right? That will release some energy, right? H nu, right? That basically transition from one particular layer to another layer, right? Like basically you are adding this electron from the excited state to the ground state, or a particularly there is one electron, whether it will absorb some energy, right? It will absorb some energy and it will jump from the ground state to excited state or valence shell of an atomic configurations to basically do some conduction, right? This kind of property. So you need this kind of A dagger or A operator. Means if you apply the basically A dagger operator, right, the raising ladder operator on this quantum state 0, so the electron will jump from ground state to the excited state equivalently. Mathematically, this is just applying the raising operator. Similarly, if you want to bring down electron from excited state to the ground state, it's just equivalent to applying the lowering ladder operator on that particular quantum state, right? Okay. So that's how these operators, although they are simply the outer vector outer product, right? Another implication on quantum computing side is we all know the entangled gate, right? Entangled gate, and you have already simulated many algorithms, right? And that entangled gate is a CX gate. How it looks like? This way: 1 0 0 0 0 1 0 0 0 0 0 1 and 0 0 1 0, right? This is the CX gate or the entangled gate. And in fact, you can represent this particular matrix. This is known as C naught or CX gate. Okay. This C naught also can be written as outer product of 0 0 tensor product with I plus outer product of 1 1 tensor product with sigma x, right? And this is the precise definition how basically your quantum state you basically prepared as an operator out in the outer product form, right? Although you cannot implement this 0 0 directly on a quantum computer, you need a CX gate directly to qubit gate. So 2-qubit gate you cannot break using some single qubit gate and simulate. That's not possible, right? But mathematically, this is equivalent to this 0 0 times identity. That means if you look this part, this is like an identity matrix, right? And if you look at this below part submatrix, right, this is a sigma x, right, the poly x matrix, right, the below part. So this is equivalent to the, you create a 4 cross 4 2 matrices and sum them. First part of the matrix is prepared with this particular configuration. Second part of the matrix, you basically flip the bit in the 1 1 configuration, and you basically sum of them, and you get the CNOT gate, right? It equivalently does if the first qubit is gate 0, does nothing to the second qubit, and if the first qubit is 1, then it flips the second qubit. So that is the purpose of this gate, second qubit, right? So we'll see more examples. So I'm giving a break of 5-6 minutes. So we'll come back at 4:15 and we'll continue. And if you have any doubt, please feel free to put here. So I have so problem in throat, so I'm going a bit slow with voice. So please pardon me today. And please feel free to put your questions in the chat box.
Yeah, thank you, sir. We'll take a break. Participants, please note, tomorrow is Saturday. So Saturday, we'll have 3 hour lecture. We'll start at 2 o'clock. Yesterday, forgot to remind last Saturday, forgot to remind you, and many could miss out the first hour. So please save or note in your, or set an alarm in your mobile phone or whatever way that you have a reminder. Set your reminder for 2 o'clock tomorrow. Tomorrow there will be a 3 hour lecture with like similar breaks, like 5-10 minutes in between, and we'll complete. So please note them. Don't miss the first 1 hour, right? So this has been facilitated so that the actual content will not be missed. We'll cover more from Dr. Mustafizur. That was the basic idea, because he is relatively free on Saturdays, but he is sparing his time on Saturday, so that's what we can. So the quiz will also be starting tomorrow. Quiz 3 will be starting tomorrow. Quiz 2 will also be open for those who missed. So please take the exams. Quiz 3 will close. 2 and 3 both will be open tomorrow evening, Sunday, Monday evening. Monday midnight will close. Maybe we'll keep quiz 3 open for Tuesday also. Quiz 2 will close on Monday evening. That is the last attempt. Quiz 1 will not be reopened again. So quiz 1 is already over. 900 plus I've taken the exam. So my target is achieved. So I will not open quiz 1 again. Quiz 2 also, we are hoping that you will complete it by Monday evening. 900 of you will take. So our target is for 900 people this time. So hopefully we'll do that. About 9,000 have registered, 970 have logged into Canvas, and 920 or something have taken the quiz 1. Quiz 2 also, I hope you all will complete those who have missed. Quiz 3, please complete it on schedule, and we'll try to issue the certificates. You'll be happy to know the 8-bar IBM logo. Mustafizur sir knows it very well. The 8-bar logo is a very prestigious logo of IBM. We have been awarded that these courses from QT-03 onwards. We have the IBM logo which will be placed. We also got permission for the National Quantum Mission logo. It will also be placed. TCS, IBM, National Quantum Mission, AICT, IIT Madras. So these all will be there on your certificate, and hopefully best wishes for you. So please complete all the formalities, and we will close because again immediately on 8th of December we are starting the QT-05. The brochure will be released today. We'll try to release the brochure and share it in the groups today. Registration is anyway open. You can register for that, right? Over to Mustafizur sir. Whenever he's ready, he can continue.
Okay, let's start. Let me share the screen. Now, we will see the some application sites in quantum communication or information theory. So I'm starting it today and we'll continue tomorrow, and we'll see how to mitigate the noise. At least one is the super dense coding. If we get time, we'll cover that, and then quantum teleportations and some other noise modeling in quantum hardware, right? Introduction to quantum noise. Noise in quantum hardware, okay? So just to start with the quantum noise part, one certain things. One is basically now your state vector is basically for the quantum information part. Quantum information. So earlier we were only dealing with real parts, right? Now it can have imaginary thing. So quantum state vectors now, quantum state or state vectors, the main differentiating part is that if you have a quantum state or a vector, it may have amplitude, say alpha 1 to alpha n, where each such alpha can be complex numbers, okay? And the norm of this state vector, the norm should be equals to 1. That means sum of all the entries alpha I for all I square equals to 1, right? So this is an important criteria for the quantum state, right? For example, suppose our state is something like this. Quantum state is 1 plus 2I, right? And by 3 get 0, right? Minus 2 by 3 get 1, right? So basically then probability of getting the output outcome as 0. So probability of getting my outcome equals to 0 is 1 by 1 plus 2I, right? By 3 square, right? Which is 9, 5 by 9. And the probability of getting the outcome equals to 1 is minus 2/3 square, that is equals to 4 by 9. So once I introduce my information in the complex vector complex numbers, so I have two quantity. One is the amplitude, right? And one is the phase, right? So the amplitude part, so if there is an error, right? So error may cause error can come from many sources, right? First is how you prepare your quantum state, that is alpha ket 0 plus beta ket 1. For example, 2-qubit system, how you prepare this alpha and beta, how you prepare the quantum state ket psi, right? The generation itself, the generation of quantum information, there may be like so multiple times you do measurement, so multiple times you create the quantum state psi, right? So there is uncertainty in not only in 0 and 1, but also in like the probability of 0 and 1, like the alpha and beta, right? In alpha and beta generation, right? Then when you transfer this information through algorithmic applications, like you reach from phi to psi using some unitary operations, right? These are quantum gates, and today we'll see that what is the implication of quantum gates, for example, right? So then this gates has something called a coherence time, right? Coherence time. So if some particular quantum algorithms has many gates, and the depth is also very high, right? The depth of the circuit is very high. What is depth? I'll define. So the depth is very high, then you are losing the coherence time, right? And that has implication in error. So the error can come both earlier in classical information. Suppose you communicate in information 000, and you got the result as 0 1 1, right? So the last bit is flipped from 0 to 1, and that is the classical information error, right? So that is called the bit error. And from where we know the term bit error rate, right? BER, right? Or symbol error rate, ACR, right? In the classical information theory. Now you have more than the bits. There is something that is basically coming because of the complex nature of the information. There is something phase informations, right? So phase there is a like a highly likely that there is some sort of error in the phase informations, right? And that is what we call the phase error or phase flip error. Mm. So what is that? I'll come in details. But main these two kinds of error are here. One is the bit error and one is the phase flip error or the bit flip error. In quantum, it is called the bit flip error, and phase error, it is called the phase flip error, right? So that means bit flip error is, suppose you transmitted 0, get 0, and you are getting get 1, or you transmitted 1 and you are getting 0. This is called the bit flip error. And suppose phase flip error is that you transmitted 1, but you are getting minus 1, right? This minus is coming as a phase flip error. So from plus 1s to minus 1, right? Which are the coefficients of the K1 vector, right? So then so that's why there are two particular gate in the computing part. One is the bit to model this kind of errors due to one is the generation of the qubit. Second is the application of the gates, because how you apply gate, because if you have an artificial atom or a qubit, say it's a LC oscillator or something, right? And it has a particular how you generate the waveform, right? Or the artificial atoms, how you create the ground state and the excited state, or if you have a like system where you create the spin state as a quantum state, like, or the photonic system, you create the horizontal and the vertical polarizations of the photon, right? And when you apply unitary matrix or the circuit, quantum circuit on in front of the quantum state, right, to basically operate on the quantum state from a vector to another vector, right? That means physically you operate something here, right? So typically it's a microwave pulse for a superconducting qubit, right? In a superconducting setup. So that means there is a like a chance of doing error of applying these gates. So these gates are not perfect, right? Then the third is, once you get this information, whether this particular qubit is interacting with the environment or not. Is it absolute minus 273 degrees centigrade or near to that? So what is the thermalizations error there? Then you are doing the measurement and there is measurement uncertainty, right? So multiple stage, there are chance of bit flip error as well as phase flip error. To model this bit flip and phase flip error, so we typically there are various noise model, but so to understand that thing, we need to know the two particular Pauli operators. One is the sigma x, which is 0 1 1 0, right? And one is sigma z, which is 1 minus 1 0 0, right? So this sigma x, what it does, sigma x, if you apply 0, so that means it becomes 1, and sigma x 1, that means 0, right? So if your information say 0 0 0 you transmitted and you are receiving, say basically 0 1 0, so there is a bit flip. That means it's you can model this as a circuit like this. So basically there is nothing means identity, there is a X gate, and there is a nothing means an identity. So this is your this bit flip error channel, right? Bit error channel, where you started with 0 0 0 and you reach to 0 1 and 0, right? Similarly, this sigma z, if you apply sigma z, you get you apply on the 0 state, you get 0, and sigma z you apply 1, you get minus 1, right? Minus get 1, right? So this is this sigma z or the Pauli z operator helps us to model phase error, okay? Phase error modeling. So now, now let's take a deep dive with examples. And there are some more gates I'm not covering. So let's take some quiz problem. For example, suppose H is Hadamard gate, right? 1 square root 2, 1 square root 2, 1 square root 2 minus 1 square root 2. Better to write this way: 1 by square root 2, 1, 1, 1 minus 1, right? This is our Hadamard gate. And there is something called a phase gate this way, phase operation. So it is 1, 0, 0 e to the power I theta. If theta equals to pi by 2, we call this gate as S gate, right? Which is a Clifford gate, p pi by 2. That's 1, 0, 0 I. And there is a non-Clifford gate for pi by 4, which is 1, 0, 0, 1 plus I by square root 2. Okay. So now a quick question is, first quick question is, if I apply T to plus state, what will be my outcome, right? So the thing is, plus state is basically if you apply Hadamard gate to 0 state, you get a plus state. Okay. So can someone answer what is the answer for this? The second question is, what is the HSH square? So quickly you can check just by doing matrix vector multiplications. Can you just try? It will hardly take 10-15 seconds, right? Why I am covering so basic things. So always you can start with black boxes, you can give input and output, but you may not appreciate why you get that result, right? That's why I am covering the very basic things. When you design algorithm, when you design circuits, right? Why you are applying a Hadamard gate, why you are applying a T gate, why you are modeling a particular error with polygate. So these are the very fundamental things related to those kind of error modeling, error mitigations things, right? Yeah. Now let's take okay, once you have done this answer, maybe you can try. So in general, now let's understand circuit depth. Why circuit depth is important and why it's a barrier for large scale quantum computation on present hardware, right? Although you can do a lot of experiments, right? Lot of meaningful result on a quantum machines right now. But when you design the algorithm to solve a particular problem, you take care of the depth, why it is so important. Suppose you start with get 0 state, right? And simply you do measurement, you do nothing, right? Then you start with 0, you apply a X gate, right? Then you do measurement. Then you apply with 0, start with 0, apply X, another X, then you do measurement, right? Suppose you do like this. Simply with X gate we are doing, right? So what is the first like if you do this measurement, so once you do measurement, so typically we do measurement in z basis, right? Pauli z basis. So what it does is you calculate the expectation value for this particular 0th state. So that is 0 g 0. Can someone tell me what is the answer here? Okay, let me show the definition. The expectation value of z hat equals to psi z psi like it's a inner product between these two, like this state and this, right? So expectation, how we calculate? If it is 0, for example, 0 g 0, so 0 state, and if you apply z to 0 basis, what we get? Plus 0, right? So plus is not required. So just 0, 0 outer product, right? So you can write this way. Plus 1 times 0. That is 1 constant times 0 and 0 outer product equals to 1, right? And then you can also check. So this answer will be 1, right? So you get plus 1. Now suppose you apply 1, G and 1, right? Expectation value of this qubit 0, and you applied X gate here. So this 0 becomes 1, right? And you are doing measurement on the state 1, right? So that is 1 Z1. The answer will be -1. You can easily check from here. You just put 1 here. So 1 G 1. So this G, if you apply on 1, it gives -1 times 1 inner product with 1. You are multiplying, you are doing dot product with the same vector. The answer is 1, right? So that is -1 times 1. The answer is -1, right? You get -1. So now you get, suppose this is your state 1, and again you apply basically X means bit flip, and you get 0, right? So you get 0, G 0 means +1. And here you will see again you will get -1. So you get answer of +1, -1, +1, -1 kind. Like this is an algorithm for even and odd number, finding even and odd numbers, right? So now how we represent the expectation value? Expectation value we represent here in this even and odd number case is -1 to the power d, where d is called the depth of the circuit. Depth of the circuit. In the first case, there was like no X gate, right? If there was no X gate, D was equals to 0, and our answer was -1 to the power 0 is 1, right? Second is the depth of, that is only one X gate, the answer is -1. D equals to 2, then our answer is again 1, then again -1. So for odd power of D, you get -1. For even power of D, like even value of D, you get +1, right? So theoretically, what we should get, and so basically, if you plot depth versus expectation value, and suppose this is your 10, depth is 10, depth is 20, and so on to depth is 100, right? So theoretically, I should get the value +1 and -1. Suppose this is 0. Right, so theoretically I should get value here and here. So like this way, I should get the value like this. My quantum information should look like this: +1, -1. It will vary between +1 and -1 like this. So you can connect these lines. So it is just varying value between +1 and -1, right? But actually what happens in the physical hardware, we don't get state like that. What we get, if we increase the depth, and because every such X gate contains some error, I will model that error. You will see that your state is oscillating, and you will get some values like this. So it will start from ±1, but slowly it will give you value towards 0. That it start losing the quantum information, right? So this is +1, this is -1, this is 0. You are measuring the same qubit again and again, right? So this loss, frequent loss of the amplitude, is called this is incoherent part due to incoherent noise. This is coming, this flip part is coming due to coherent noise. We'll study the coherent noise today. And there is something called, this particular part is the, when you do measurement, right, you do projection, right, whether on the 0 state or on the 1 state, due to measurement, you get another level of error that is called the projection error. projection error. When you measure something, it always lose information. Okay. So, so like energy decay, phase error, and all these terms are related. So now let's have a quick questions quickly. Suppose we start with this quantum state at 0, right? In the blosphere. In the blosphere. Suppose this is our blosphere. And so that, can you tell us what is the, if you do measurement on z-axis, what is the answer? Measurement on x basis, what is the answer? Measurement on y basis, what is the answer? Right? For so for the state 0, for this state, and if it is in the state 1 state, and you do the same thing, your observable is G, your observable is X, your observable is Y, right? What is the answer here? Can somebody tell me? This should be 100, this should be -100, right? By just simply visualizing this, you can also say this is just in the z-axis, right? And this is your x-axis, this is your y-axis, right? And you can also calculate this x also, because x is defined as your Pauli x operator, right? And you put 0, like 0 x 0, you can calculate, you will see the answer is coming at 0. For the y also same thing will come. Now now so let's see the evolution, time evolution part on the blosphere, right? So I am taking very small simple circuit with only Pauli X gate. When you will study quantum physics problem to solve on a quantum computer, you will see like XXG model, XXY model. This will be your Hamiltonian, right? These are called interaction Hamiltonian. Today I am taking Hamiltonian with no interactions. Very simple Hamiltonian. For example, suppose you're starting with this state, gate 0 state, right? And you apply X gate, right? So once you apply the X gate, so what is happening? You are reaching this particular vector from here to here. So that means you have a transition like this, right? Anti-degree transition like this, just by applying the X gate, right? So you are getting gate 1, right? And once you apply like another level of like 0, you started, you applied X, you applied another X, right? Mathematically, of course, X into X is identity matrix. But on the information side, so on the information side, so you are back to the original state. Earlier, you were here. So that means you have a two-level transition. One is by you went from here to here, and then again you basically travel another pi by another basically 180-degree thing, right? A 90-degree rotation around x-axis. Um, so this kind of rotation we do because this is our now x-axis, right? So around x you rotate, and suppose let us define our Hamiltonian. Suppose our Hamiltonian is simply this h bar omega Planck constant times omega by 2 x. This is a very simple Hamiltonian, right? And this is basically equals to h bar Planck constant, omega is the angular momentum by 2, and x is basically 0, 1, 1, 0. The purpose of this Hamiltonian is to just rotate around x-axis. That's all, nothing else. Okay. And we want to design a quantum circuit to represent this, right? So by if this is my Hamiltonian, so my Schrodinger equation is saying I del t xt equals to h of psi t, right? And if I solve this equation for the isolated quantum system, my solution will be my evolved state, psi t evolved state will be equals to u into psi 0 state, right? Psi equals to your initial state, right? And this u equals to e to the power minus I h t, just by solving this PDE equation. ODE, in fact, ODE with respect to time, ordinary differential equation with respect to time, right? So I need to implement this part. This is my quantum circuit part, right? Circuit part. Because I'll start with this particular quantum state, right? I'll basically start with psi some 0, right? And I need to design a quantum circuit such that I evolve in the state QT psi t, right? So this is my solution of the Schrodinger equation. So now, 2-3 things. First is x had square equals to, that is x is the Pauli operator, x times x, right, equals to identity. And x, if I apply 3 times, so it's basically x had and x hat, it is equals to x hat, right? This is one important relation we need to remember. Now suppose we define theta equals to omega t, right? Just the angular velocity times t, right? And then there is a gate, quantum gate, that is called Rx theta. The gate is e to the power minus I theta by 2 poly x. Right? This x is the poly x. This is a matrix basically, right? So that means this is equivalent to like this. So instead of this 1, right, you write e to the power minus I theta by 2 here. There is a x, right, e to the power theta by 2, 0, 0, right? Something like this. Yeah. And then you can also no need to represent this way. So matrix part we eliminate. This is just for our understanding. This can also be written as cos theta by 2 identity minus I sin theta by 2, just by Euler expansion, right? By 2 x poly x, right? Now from this relation, we can also write it as x hat to the power n. It can take 2 values, identity, or it can take values n, right? This is for even. This is x hat. This is for even. It can give identity, or it can give x hat for odd, right? For odd values of n, right? These are the 2 consequences, and we'll use this here. So anyway, if you expand in Taylor series, you get some even terms, and for this e to the power part, right, you get some even term corresponding to cos theta by 2. You get some Taylor series expansion of these e to the power terms. If you get some odd terms, and odd terms come here. And for the odd terms, if you see odd terms, if it is odd, then it is equals to just simply a single Pauli x vector, right? And for the even part, it is only identity part is coming. So it's a direct consequence of this theorem, right? And now ideally this is fine. There is no issue, right? So for example, if certain case, let us understand, if theta equals to 0, so theta equals to 0 means sin theta by 2. So you can see sin 0 is 0, right? And so this part is out. Only this cos theta part is here. So cos 0, so it will give you identity, right? Your Rx theta will be identity gate. And if theta equals to pi, we get 0 minus sine pi by 2 x, so which is equals to minus ix, right? So this is the some global phase that will come into picture, right? So mathematically earlier it was nothing, just you are doing a rotation like this from the same positions, but actually there is a add-on global phase coming due to this rotation minus ix on the blow sphere, right? and we'll see what is the complication for this, right? So this will like back to origin will be the case for 2 pi rotation. This is for the pi rotation, means you come from here to here. This is the pi rotation, and this will happen by 2 pi rotation, right? So now what is the consequence? What is the problem with this? Everything is so ideal, right? Now, because initially I told that no quantum gates are basically ideal gates, at least till now, right? So there might be some sort of error, like due to coherence time of the qubits, right? So so suppose our ideal gate is like this. This is our ideal gate, and suppose this is our real gate, x tilde. Suppose this is real, right? So when I say real, that means my definition of x tilde is no longer Rx theta. Now this is Rx, suppose pi plus epsilon. Suppose theta equals to pi as an example, right? Okay. So and for real case, and for real x is suppose Rx this pi. Okay. So now this part you can easily quickly check that once you do the time evolution here, right, and you apply this x tilde gate. So my answer is e to the power I. Immediately it is pi plus epsilon, right, by 2x, right? And this is equals to, I can write, because this epsilon and pi both are acting on this same matrix x, so I can safely divide them into 2 parts because they are commuting, right? So this part is e to the power I pi by 2x minus I epsilon by 2x, right? And these are like commuting terms. I just broken into 2 parts, and you can safely write it is as Rx epsilon and Rx pi, right? And this part is basically your x gate, right? So so this is like some x epsilon you can write, and this is x. So x tilde gate you can write as a combination of hidden particular gate application x epsilon, and there is a ideal matrix x, right? Ideal circuit and your noisy circuit that is present inherent to the quantum system, right? So this part is noisy part. This part will be there in the noisy hardware, right? And x is the ideal operation that is there, right? So for example, if it is any arbitrary operation instead of the Pauli x, so Rx theta, and there is some this phi, that means your target is to reach from this quantum state to this particular quantum state theoretically. This is the amount of theta, but somehow how due to imperfections you created another epsilon angle here or phi angle here, right? So due to imperfection this will happen, right? And immediately it will be Rx theta times Rx phi, Rx phi, right? So it will be a multiplication of the quantum gates, right? So so now um, now it has a huge implications in the suppose you design many such quantum circuits, right? Suppose this is like up to dth depth is d, right? So immediately your total evolution will be, ideally your total evolution should be x to the power d, which is Rx, this is pi and power d, so this d will come here, right? And but due to noise you tilde total, right? Due to noise or the noisy versions, right, of individual, every gate had some error, right? So u tilde is x tilde power d, right? You are applying for d, right? So Rx epsilon and Rx pi, if your theta is pi, right, all to the power d, then this is equivalent to Rx d epsilon times Rx d pi, right? D pi, this part. Now U tilde total will be Rx d epsilon times U total. Now this phase, very small phase epsilon, because of the many quantum circuit component, like many quantum gates, they accumulated together as a multiplying factor in the phase. And this is a huge or critical implications due to this simple X gate, as an example we have seen, right? And there are lots of like this is a critical part now because of the, so D is now important. Suppose you have a problem P, you apply a quantum computer, right? Quantum algorithm or a quantum circuit on a quantum hardware, and you get a result R. If this R contains huge error, right? Then what is the utilization of a quantum computer, right? So that thing comes here. This how complex your quantum algorithm is, how you design your quantum algorithm means how you design the unitary matrix U, and that U has contains so much d epsilon terms, right? And how you mitigate that, right? So let's take an example, quick example, and we'll close it quickly. So suppose I start with this state, right? X, and I apply D times, and I do measurement, right? So my answer should be right. So which is equals to cos d pi, that is -1 to the power d, right? Because for Pauli gate the angle is pi, right? So um, so ideally this should, the plot should give ±1, that the graph I already told. So you increase the depth, and if this is your expectation value z, right? So you get +1 -1 +1 -1, this kind of answer for various depth, right? So suppose this is your 100, this is your 50, this kind of gate. But once we have like x epsilon part here, hidden noisy gate, right? And the ideal is x, and you do the measurement, right? So now your result will be cos d pi plus d epsilon, right? And suppose epsilon equals to only 3-degree phase error, only 3-degree phase error, right? Then also you will see, as you increase the depth d, and you basically implement this +1 -1, this expectation value versus the expectation value versus the depth, or depth versus expectation value, it is no longer +-1, so it basically oscillates. And you can do an experiment and check up to how much gates you can give, and then you start losing this +-1 state, right? So this is around 40, this is around 85, something, that kind of answer you will see, right? So this is due to, then you can easily check that error is basically proportional to depth. And this is an easy experiment, right? So quickly, I'll show a Qiskit implementation of things. I already wrote the code, and I'm just sharing you the link so that you can check the code yourself. Also, just allow me 1 minute. I should share the code link. Build noise model. So I'm giving the links, Qiskit links, in this chat box. This is one link, and I will share the another link. Okay, there is okay. Okay, the another part is not there. I'll show here in this thing, and I'll share the notebook, Jupyter notebook, with all of you. Okay, so if you have till there, if you have any question, please feel free to put in the chat box. I'll share another screen now. Just 1 minute. Let me open this VS Code. Um, so I just like check the Qiskit versions, right? Like these are just ready-made code. Like from Qiskit import versions, you will see the versions of the Qiskit. Now I define two vectors, ket0 and ket1. Okay, and the ket0 is basically 10 and ket1 is 01, right? And let's print these two states, and basically ket0 and ket1, and I have done the like their probabilistic representation, like half and half, right? Ket0 by half and ket. So you can directly print the original value also, like it will be 1 1, right? Something like that. So now I define certain matrices like 1 1 0 0 and 1 0 0 1. These are the matrices, measurement matrices I defined in the class today. So, and some other matrices I also define, like in ways how you define various measurement operators, right? And you can simply like check, like you started with a 1 0 state, then you apply a particular measurement, then what is the output, right? And I just printed this in latex form, so you can do those kind of experiments. Then there is something called state vector in the Qiskit info module, right? You can use the state vector module and define your same quantum state vector in this form, right? The component of the vector, and it will directly give you the quantum state representation of those vectors. And once you do that, then you can, using the Qiskit info module, you can check that the state vector you designed, like u, v, and w, you can easily check whether that is a valid quantum state or not. For example, I define u as 1 by square root 2, 1 by square root 2, and it's saying that it's a valid state. For w, I defined 1 by 3 and 2 by 3. If you do the square of 1 by 3 and 2 by 3, if it is not equals to 1, then it will show that it's not a valid quantum state, right? Now I do the measurement, right? And this measure, basically v dot measure is a basically a function that will do the measurement, and that I call from, just let me check. Okay, that is available in the Qiskit module itself. And you can do the measurement, and you can post process the result. So for this particular above qubit, right, you can check what is the measurement. So it will give one of the state like 0 or 1 with what probabilistic state, like so there are some examples, and if you do like multiple such measurements, you can also see what is the, like after say 1,000 experiments, what is the statistics, like how many times the 0 state is coming, how many times the 1 state is coming, just by repetition error. So because the states are erroneous, right, you are not getting the 100%, like 500 times 0 and 500 times 1. Although initially I started the state with 0.5 0.5, but now you can see the probability is changed, so there is a decaying thing, right, due to error. And now there is a state evolution, very simple state evolution using Hadamard, T gate, H gate, S and Y. You prepare a state, and like this H, T, H, S, Y, and then you evolve that state, and then you do the measurement, and you see, can you basically manipulate the probability to increase the probability in state 1 and decrease the probability in 0, because you try to design an algorithm to emphasize the probability, right? The initial probability distribution is something else, but the ultimate probability mass functions the distribution, right? That you want something where your solution state should have higher probability, right? So these are just very simple toy examples for basically manipulating probability doing quantum interference, etc. There are some more examples. So I'll share this code book. You can just quickly have a look. And this is not difficult. And for specific to noise model, I have provided some this thing, the like Qiskit handbook link in this chat box. Okay. Yeah, I'll be sharing the notebooks. Don't worry. So it's not difficult. So yesterday, like last week, I shared some very basic linear algebra notebook, and today I'll be sharing at this studio. Tomorrow I'll be sharing all the this Qiskit noise toolbox, quantum information toolbox with all of you. So with this, I'm closing the session today, and tomorrow I expect to start something more on the quantum information side, use of the probability theory and quantum teleportation stuff. And if time permits, we'll also see a very basic repetition, quantum repetition code for error correction.
Thank you, Mustafizur sir, for the detailed explanation. And so hopefully participants, we will share the slides, and please remember that tomorrow's quiz will include sir's lecture tomorrow also. So you may plan to take the exam tomorrow, or basically prepare and take the exam on Monday accordingly. So there is one small change, because we mentioned that quiz 3 will be considering till November 22nd. So yeah, November 22nd. That's so till November 22nd. That is till tomorrow. The content will be considered to take the exam. Yeah, there is some chat. I thought chat. Right. Tomorrow's session.
So again, it is a gentle reminder that tomorrow's session will be starting from 2. So we will be basically putting this again in the WhatsApp group, but whoever has joined, kindly mark it that tomorrow's session will start from 2.
Yeah, the Jupyter Notebook is Python. When you execute, you can use Jupyter Notebook to run the Python code. So just Google up Jupyter Notebook. It is Jupytr, Jupyter Notebook. So just then you can set up easily how to set up Jupyter Notebook, and then you can run Python codes in that, right? Cloud limited to 1 month duration. What is cloud? You are saying Canvas material. Canvas material will be there till December end. We will extend it again. एक बार देख लेना उनका क्या नाम है. IBM Cloud is, once you get the login, it is available. I think as of now they are giving 10 minutes this thing, quantum time.
Yeah.
For execution.
So those who are like starting the quantum computing, initially learning things, I'll suggest you directly use the simulator like state vector, ER simulator. This kind of simulator are there on IBM side. You don't need to even have an account. You can simply just install the Qiskit in your Jupyter notebook. You install Qiskit and you simply do the code. Once you are ready, like you have some problem in mind, you want to do research, you want actual hardware, you create an account to IBM Cloud, use the IBM hardware. Then only you are confident that you already run your algorithm up to 10 qubit, 20 qubit on a simulator. Then you want to go above, you use the hardware. Okay. So because hardware means price, so somebody is like, it's not about IBM, any company, if you go, or any person, so they are basically like, you are using hardware means basically you are like, every hardware every second is priced there, right? So it's a huge cryogenic setup, lots of energy invested, lots of people invested, right? R&D invested. So this is dedicated for when you start doing research, right? For learning purpose, just a simulator is enough.
Yeah,
But of course, if you want to get flavor of real noise, real things, hardware is necessary. Okay.
Collab, there is a question, sir. Can we do
Yeah,
it on?
Collab, yes. Collab is like cloud, Google Cloud access, free access for Python. If you have good internet connectivity, you can directly open a collab, and there you can install Qiskit and all. Only catch is every time you open the collab, every time you have to install all the packages. That's the only problem. Otherwise, no issue. But it is always good if you install a offline mode like Anaconda, Jupyter, Spider, VS Code, anything in your laptop. Even if you don't have internet, still you can code, right? And then once you install, you don't need to reinstall again the same packages, both for Python or Qiskit packages. Yeah.
Qiskit, Jupyter Notebook, please just browse. It's very easy. Once I
It's very
started
easy and
working,
all are free, sir. All are open source. All are free.
all are open
Qiskit
source.
free, Python free, all are free.
Just type Jupyter Notebook, how to install Jupyter Notebook on Google, few steps within 15-20 minutes you will install. And most of the, in fact, Qiskit actually writes the whole thing in the Jupyter Notebook only. The explanation is there, then the code is given. So you can also look at, and some tutorials on Python also give you that mode. They teach the content on the Jupyter Notebook text part, and they'll give you the code where you can immediately execute and see. So Jupyter Notebook is nothing but editor, you can say, or what we call API, something like earlier days we had Eclipse, now you have Jupyter Notebook. That's right.
Somebody is
So
asking an interesting question. Is simulator enough for PhD thesis or something like that, right? It's up to you. If you have like very good theoretical work, you propose something like source algorithm, and you are confident with theoretical proof, you don't need a hardware. But in general, if you propose something for real time application, real life applications, and you demonstrate something that you are doing better than classical or something like that, or at least hybrid something you design, then you need a hardware. Like, so any real time problems, you need to show real results, right? Then hardware. If you want to do something very theoretical hypothetical work, or something very concrete in the theoretical way, you don't need a computer also, just pen and paper is enough. Right.
Sir is talking about IIT Kharagpur PhD. But yeah, for you, if you're looking at a Scopus paper, I think simulation will be sufficient.
Right.
But then as you look at, there are various levels of journals. So if you want to get into a good journal, then you
Right.
will have to do a
Exactly. So if you are publishing with good IEEE transactions or nature journals and all, most of the time, if you propose some algorithm for real life application like biology or like biotechnology, chemistry, or even engineering problems, they will ask you to simulate on higher qubit size or demonstrate on the hardware how the result is coming, what is the fidelity, what is the circuit depth, how you executed on how many qubits, what is the classical result, what is the quantum result, how good or how bad they are, is there any theoretical bound or any empirical results that you can show, right? So these kind of questions will be asked in these good journals. Yeah.
नीचे करो slide start. Yeah, so the basic idea is about what do you say? Yeah, you can use Collab Pro and other things if you want to do it. But as Mustafa sir mentioned, first, if you are in the beginning, do the simulations, run it out. And then once you are successful with that, then obviously you will know what to do next. Then you will understand. So please take it that way. One question, sir, researching on ROI optimization using quantum agentic AI intersection.
What is the ROI?
The
Full form?
problem, return on investment.
Okay. Quantum finance or something like, okay. Researching on array optimization using quantum and agentic intersection. So what is the question?
Question
Okay.
is it going to give return on investment for me? The time I spent. I think that's what.
Yeah,
Yeah.
I am not the best person to answer this question. Maybe you can ask this kind of question to Venkat sir or somebody who is more
Yeah.
experienced. Okay. Yeah.
Okay. Yeah. So see, once you start the doctoral thesis, you are the best person to answer
Right.
the question because you will read more about it. But yeah, quantum and agentic AI intersection, AI and quantum, definitely, if you combine them,
Right.
wherever GPUs are stopping, wherever your what do you say, supercomputers are not able to
Uh,
do.
So
If you are
in general, there are two things. One is, um, why you need a quantum computer? Quantum computer gives you a very big Hilbert space. Okay, if you have 10 qubits, you have 2 to the power 10 possible states, right? If you have 100 qubits, it's give 2 to the power 100 number of Hilbert space. How you use those quantum samples or the values you are getting, does a very high dimensional space giving you some advantage to AI problem? That is one part. Second is the quantum computer gives very good samples, which classical computer may not produce, right? Can you use that samples on your HPC side, like classical side, to utilize for better pattern learning or better like regression problem or better pattern identifications, right? Classification. So it's one part is how you create a bigger feature space or higher feature space, and then how you post process like the AI part. AI part is basically learning part, right? So basically directly on the classical side, you have an input and output, and you create certain feedback loops or network between input and output to find the relations. Now, if you put a QPU, quantum processing unit, and you increase the Hilbert space and you increase the feature space, but does it give you some advantage or not, depends on how you invent the algorithm, how you design the algorithm, how you take the best part of AI and quantum together, right? So this is not guaranteed, but you can have a good research around that, right?
Yeah. Good. Thank you. So we'll take a break. We'll meet tomorrow at 2 o'clock. Please note the timing. 2 o'clock, we'll have 3-hour lecture, 1 hour every 1 hour, and then we'll have some break each time. Right. Thank you so much, Dr. Mustafizur. We'll meet tomorrow. Thank you all participants, and thank you for staying till the end. Thank you.